Okay, let's dive into this. Welcome to this explainer, where we're going to unlock one of the absolute most powerful concepts in modern AI. Building agentic AI by mastering RAG pipelines with the Pinecone vector database. If you've ever found yourself wondering how enterprise-level AI can just instantly access and understand mountains of private company data without just, making things up, well, you are in exactly the right place. Today, we're taking a really structured, step-by-step journey from raw data all the way to a fully functioning AI pipeline.
To kick things off, imagine I hand you a massive 1,000-page book with 1,000 different stories in it, and I ask you to find one highly specific detail. If you just start reading from page 1, it's going to take you hours, right? Maybe even days. But what if I just gave you the exact page number? You'd flip right to it in seconds. This book analogy perfectly captures the massive speed advantage of using AI vector search rather than forcing a system to read raw text from scratch every single time you ask it a question. We're going to rely on what I like to call the library-to-librarian mental map to understand exactly how this whole thing works.
So here is our roadmap for today. First, an introduction to RAG. Second, what are embeddings? Third, the Pinecone vector store. Fourth, cosine similarity. And finally, building out the complete RAG pipeline.
All right, Section 1. Introduction to RAG, Bridging the Data Gap.
Now, you might be wondering, aren't large language models already incredibly smart? And yes, they absolutely are. But they have a massive blind spot, your private data. RAG essentially bridges this gap. And actually, what's really interesting here is that it clears up a huge point of confusion for a lot of developers, the difference between searching and generating. Let's look at a simple greeting like salam. If we run this through a vector search, the AI is purely looking for semantic similarities. It's going to return words like hello, hi, or greetings. It's literally just matching meanings. But if we pass salam to an LLM like Gemini, it takes on the role of a conversationalist. It actually generates a logical response, replying with wa alaikum assalam. So, in short, vector search finds, while LLMs respond.
Moving right along to Section 2, what are embeddings, and how do we translate language into math?
So how does the AI actually go about finding things? How does it read our data? Well, at its core, AI doesn't understand English, or any human language for that matter. It literally only understands numbers. Embeddings are simply the process of translating our natural language text into long lists of numerical values, which we call vectors. Just think of it as translating that 1,000-page book into a highly organized, easily searchable numerical index. To ground this highly abstract concept into something a bit more relatable, let's use a visual analogy, the toy box. Imagine you've got this massive pile of toys. You decide to assign a unique secret code to all the toy cars and a completely different secret code to all the soft teddy bears. Now, when the AI wants to find a car, it isn't physically looking at the toys. It just scans for that specific secret code. It naturally groups similar items by matching these codes, instantly finding the right box of information. So, you're probably asking exactly how long is this secret code? Well, in our specific implementation, using the Google embedding model, that number is exactly 768. Every single chunk of text you feed into this model gets mapped out across exactly 768 distinct mathematical dimensions. It's a staggering amount of nuance, but it allows the system to instantly understand complex semantic relationships without completely overloading the database.
Which brings us to Section 3, the Pinecone vector store, where we're storing those 768 dimensions.
Now that we've got our 768-dimension vectors, where do they actually go? Obviously, a standard spreadsheet isn't going to cut it here. We need a highly specialized environment. And a really great question came up in the source material about this. Why do we store this data as vectors instead of matrices? Honestly, the answer boils down to pure speed and efficiency. Matrices introduce way too many complex dimensions, which drastically slows down your search efficiency. Vectors, on the flip side, are just single lists of data. By keeping everything in a single row or list format, we perfectly balance storage efficiency with hyperfast searching. This is what lets the database scan millions of records in literally milliseconds. So the crucial point here is how we actually build this out in code using LangChain and Pinecone. It's a very precise 4-step workflow. Step 1, we securely initialize the Pinecone API using our secret keys. Step 2, we use the Google model to create our 768-dimension embeddings right from our text. Step 3, we take those newly created document vectors and add them directly into our Pinecone index. And finally, Step 4, our database is officially primed and we are ready to perform a search. Next up is Section 4, cosine similarity, or the math behind the search.
But how does that search actually function under the hood? Remember, it's absolutely not matching keywords. It's using geometry.
Cosine similarity is a metric that calculates the distance between vectors by measuring the actual angle between them. Just imagine two lines originating from the exact same point. If the angle between them is a tiny 2 degrees, they're pointing in almost the exact same direction, meaning the semantic meaning of those words is incredibly close. But if the angle is 45 degrees, they're way less related. The AI simply scans the database for the vectors that form the tightest possible angles with your user's query. And within our code, we actually have specific parameters to control how this search behaves. The similarity search function is what retrieves the top K relevant documents, meaning you can just tell it, hey, bring back the top 2 or top 5 closest matches. But it gets even better than that. We can use a filter to narrow the search down by metadata. Say you only want results that originated from a specific tweet or a particular PDF. The filter guarantees that pinpoint accuracy. Finally, similarity score returns an exact mathematical match score out of 1. That exactness is a total game changer because it lets you know precisely how confident the AI is in its retrieval, something that is absolutely vital for developers who need hyper-reliable data.
Finally, Section 5, the complete RAG pipeline, where we connect all the pieces.
Okay, so we've built a library, we've organized all the books, and we have a hyper-fast retrieval system in place. Let's move to the timeline and see how this actually builds out seamlessly. Point 1, the user types a question. Point 2, the system instantly converts that text query into a 768-dimension embedding. Point 3, that embedding gets sent over to Pinecone, which runs a cosine similarity search, finds those tightest angles, and pulls the exact relevant context. Point 4, we grab those search results, combine them with the user's original query, and pass the whole package over to our LLM, like Gemini. And finally, point 5, the LLM reads all that context and generates a highly accurate, totally customized final answer. The librarian fetched the exact right book, read the exact right page, and answered your question flawlessly.
And boom! Just like that, you have a fully functional RAG pipeline. You've officially bridged the gap between your private, siloed data and massive language models. But as the instructors in our source material teased, this is really just the foundation. Think about it. Now that the AI can actually read and retrieve your data, what happens when we give it the power to do things, to click buttons, trigger APIs, and automate complex workflows? Well, that leads us directly into the next logical step of Agentic AI, function calling. How exactly will giving your AI hands completely change the way you build software? That's something to think about. Until next time, keep exploring.